and share my screen. Okay, so now you please let me know if you can hear me and you can see the screen.
Yes, you can.
Good. Okay, so I wanted to do a couple of things today. First of all, I was a little bit surprised on the result of the midterm test that not so many people actually did solve the problems that you had. So I will probably go over one of the problems now just to demonstrate that it's not something completely unsolvable and difficult, and also to refresh our memory on like some functional programming concepts. And then I will switch to talk about logic programming and also show a few examples because we don't have too much time in our course left. In terms of the end of semester, I think we have like next week would be our last lecture, right? Our last meeting. So I will dedicate this time to kind of Q&A. So today I will give you one more logic programming lecture to watch, and we will not have the logic programming lab, but we will have problems on logic programming as part of the final exam. So next time would be like Q&A. We'll meet online and you will be able to ask any questions that you have. And then for the exam, I think I'm not sure about the final scheduling, but sometime around 25th of December, we would probably have this final test. And by next week, I would also, of course, have all the marks for labs available in the spreadsheet so that you can clarify all questions that you have. So that's the plan for the rest of the term or the rest of the course. Let's go over any questions that you have on this. No questions. That's good. So let's go over one of the problems about the tree. There was a problem where you have to print all leaves of the tree together with the path to the leaves. So something like, let me draw. So something like this. You have a binary tree. Like this, 1, 2, 3. And you're supposed to produce a sequence of leaves, of leaf values. So leaf 1 and path to it. And path is constructed from letters L and R. So leaf 1 is has the path LL, meaning that we have to go to the left branch and then to the left branch again to obtain this leaf. So 1 LL, 2 LR, and 3 R. So you're supposed to produce a sequence like this from the tree. That was one of the problems in the midterm exam. So let's see how this can be done. First of all, whenever you see the tree problem, you should define the data type. And that's even if you don't know how to solve the problem, if you define the data type, that will bring you some points. So that is something you should definitely do, even if you don't know the complete solution up to the end. So to define the data type for tree, we can, like, there is no built-in data type, so we can define the one that corresponds to our needs. So for example, in our case, we need integer tree, and we need only leaf values. We don't have values inside the nodes. So we may just say that node would be just collection of 2 subtrees, right, left and right, and then the leaf would be integer. So that could be our data type. It's not how we normally would define the binary tree, because normally in the binary tree we would have the value corresponding to each node, and we would have empty tree as well. But in our case, if we don't need the values corresponding to the nodes, we can define this kind of shorter type. And for example, we can define some tree here. Let x equals to node of leaf 1. I am defining the tree which I drew previously on the whiteboard. So leaf 1, leaf 2, and then leaf 3, something like this, I think. That would be an example of a tree. Now we need to define a sequence that will traverse a tree. And for simplicity, let's start without the path. Let's just define the sequence that will traverse a tree. If we want to write a function that will traverse a tree and print the result, it would be just a simple recursive function. So we can say let rec tr of x equals, and then we can see what can the tree be. It can be a leaf of x, in which case we would print the leaf, or it can be the node of L and R, in which case we need to traverse both subnodes, right? So we need to say TRL, TRR, and that would be the simplest tree traversal. If I now run TRX, I would get 1, 2, 3, the value of leaves. That is, I hope, clear, right? This is simple tree traversal. Now we want to turn this into a function that produces a sequence. So if we want to produce a sequence, what we will do, we will turn it into a sequence expression like this. And instead of printing, we would say yield. Yield x. So what yield does, it returns the next element of the sequence, right? It's very similar to yield in Python, like in any languages that has generators. So here, yield x would return us the value of the leaf. But also, like when we traverse right and left subtrees, we need to yield something. So traversal of a left subtree, it yields the whole sequence. So here we say yield, but because we need to we need to yield not just one element, but the whole sequence, we say yield exclamation mark. And here we say yield exclamation mark of the right subtree. And that's it. So if we define the function like this, it will return the sequence of integers, and here it is, the sequence of 1 to 3. Now the only thing that remains is to provide a path, some path to leaves. So we would also pass the path here, and we will return this path together with the element, right? So we'll say yield x p. And when we traverse left and right, we just need to add some value to the path. So I would say p plus L when I yield the left subtree, and I would say p plus R when I yield the right subtree. The only problem is what's wrong here? Yeah, because I forgot to say TR. Here it is. What is wrong? So I have the problem because what is the problem here? Anyone sees the problem? Of course, the problem is that I'm not passing the path to. I need to pass the path to. Sorry. Traverse p plus l, and traverse p plus r. For some reason, I got confused. That's the correct definition, and here we have the what? Not the correct definition. Yeah, and here we need to provide the initial path, which is empty string. This gives us the sequence of elements and paths. So that's the problem. One of the problems, I think that was one of the most complex ones. And I kind of expect you to be able to handle problems like that in a reasonable short amount of time. So for the final exam, please also make sure that you understand how to work with trees, you understand how to work with sequences and lists, because that would be a problem on functional programming. That is not a very complex problem. So just to mention that normally at the final exam, I try to give some problem which is like not easily at least searchable in the internet, and which is more interesting than this. This is a very typical exercise. So when you prepare, try to think like how to represent expressions as trees. Like make sure you know how to compute expressions as trees. Make sure you know how to manipulate expressions like postfix notation, prefix notation, to be able to convert from, for example, from a expression in the prefix notation into a tree, and vice versa. Those kind of things. Make sure you try to do that and you know how to do that. So the idea of the prefix notation is that if you have an expression and you want to write it as a sequence of characters, like as a list, like you can write the normal infix notation is when you write 1 plus 2 times 3 and so on, where you have operator in the middle, and that is not convenient because you need to have the priority of the operators. You need to agree that, for example, multiplication happens first if you don't put brackets, and you need to put brackets to specify order of expressions. And that's not convenient, so it is much better and clear if we write, for example, operator first, which is called infix notation. In this case, if I write something like times plus 1 to 3, it means 1 plus 2, and then times 3. And it is clear that for multiplication, the first argument is this one, and the third argument is, and second argument is this one. And for plus, we have 2 arguments that follow. And this does not require brackets because it's clear from the expression the order of operations. If I want to say 1 plus 2 times 3, I would say plus 1 times 2, 3. And that would correspond to different order of brackets. So this one is 1 plus 2 times 3, and this one is 1 plus 2 times 3. And seemingly postfix notation is when you write operation after the arguments. So in postfix notation, this would be 1, 2 plus 3 times, and this would be 1, 2, 3 times plus. So those kind of expressions, like in prefix and postfix notation, you can represent as a list of arguments and operations. So if you want to properly represent this, you would probably need to define a type like type. Well, I would leave it for you to think, like till next time maybe. Think how you would represent the expression like this properly in F#, like what types you would need to put in, and so on. And I would answer any questions that you have next time. Just to practice like thinking in terms of abstract data types. Okay, any questions on this before I switch to logic programming? Are you still with me?
Yes.
Okay, cool. So in terms of logic programming is one more paradigm that we learn in this course. Unfortunately, I kind of underestimated a little bit the amount of time that we have. So we will not do a lab. Normally, we're supposed to do the lab on logic programming as well. And I will probably share the link with you. So in case you want to spend some time and do the lab, you are more than welcome to do it. And that would probably count towards like slightly higher mark, but that's not, I would not make it required because we do not have enough time for you to do it properly. So logic programming is much less, you would probably not meet it too often in your career. Like it is very good for certain tasks, but not it's not very frequently used. So it is interesting as a paradigm to understand how we can marry logic and computations. Because the idea, you know that behind functional programming, we have lambda calculus. And lambda calculus is a way to formally describe algorithms. And based on this way, we can define a programming languages, and that forms the basics of functional programming. For logic programming, similarly, we can base programming language on logic, on first predicate logic. But there is a problem that first order predicate logic is not computable. Like it can be proven that you cannot check arbitrary expression in predicate logic and to see if it's true or false for all interpretations. So that means that you cannot create theoretically a programming language that will be as powerful as first order predicate logic. So what we need to do, we need to somehow simplify the logic behind it. And for those of you who want to go into details, I would provide a couple of links to lectures that go into detail on how we can limit the logic to support computations. But to put the long story short, we limit logical expressions only to a certain form of logical expressions when we have a conclusion from a conjunction of arguments. So we say if A and B and C, then D, and those kind of expressions only. So we do not have conclusions with negation. So we cannot say if A and B and C, then not D. We will not consider expressions like that. We only consider simple expressions if A and B and C, then D, which are called Horn clauses. And Prolog as a language supports those expressions. It also supports negation in the left-hand side. So you can say if not A and B, then C. But this negation is somehow slightly different from logical negation, and we will not cover that in a lot of details. But doesn't really, it's not really that important at the moment. So we have those kind of simple expressions. What kind of programs we can write with this? So this is one example that was shown in the lecture that I gave you to study last time. So suppose we have kind of database for students who study different subjects. So we can say that Petya studied mathematics, Vasya studied German, and so on. So this can be defined as a predicate like this. So studied Petya mathematics means that Petya studied mathematics. That also corresponds to a kind of relational table. Yeah, you can imagine that we have the table which says Petya mathematics, Vasya German, and so on. So we can interpret it as a table in our head, a table of facts. And those things are called facts. And then from those facts, we can write some rules. So we can say somebody X studied technical subjects if this X studied mathematics. So here X is a variable. and the fact that it's a variable is clear from the fact that it's capital letter. So if we write capital letters, those are variables, and variables they do not have any assigned values. So it's not the piece of memory where something is stored. It's not even the substitution for the expression like in the functional programming. So variable is only valid when I start running queries. So for example, so how to use this program? The program consists of facts and rules. So what I can do, I can take those facts and rules and I can say I want to load this into Prolog engine. I say load document. This is Visual Studio Code with installed Prolog extension. So I say I want to load this into my Prolog engine, and here below you see that there is some kind of expression. It loads the text into the interpreter, and then I can query it. I can say, okay, I want to know who studied technical subjects. I would say studied technical Z, technical, and it would give me like Z equals Petya. And then if I want more solutions, I would press semicolon, and it would give me one more solution, Z equals Petya, and that's it. So how Prolog would handle this query? It would try to match this query to the rules that it has. So you see that when I see studied technical Z, it sees that there is also a rule called studied technical X. So naturally, to compute this rule, I need to substitute X for Z into this right-hand side. So it would substitute the query with studied Z mathematics. And then it would go and query all the facts. So it would say, okay, studied Z mathematics. Who studied mathematics? Okay, we have the fact that studied Petya mathematics. So that's why we need to return Petya for the result. And that's how the first result is obtained. And so on. Okay. And then on top of those rules, I can build more complicated rules. Like I can say specialty X is tech translator. Somebody X can be technical translator if he studied languages and if he studied technical subjects. One of them, one of the languages, one of the technical subjects. Somebody X is a programmer if he studied mathematics and computer science, and so on. And I can put more complicated rules on top of that as well. So that what it allows me to do now. Once I have those rules, I can query it in a different way. I can say specialty Petya X, and it would give me all possible specialities for Petya. So technical translator, and programmer. The fact that it gives technical translator twice is because Petya studied two technical subjects, mathematics and computer science. And Prolog can arrive to this conclusion via two possible paths in the deduction tree. I can also say, okay, I want to know who can be technical translator. It would give me X equals Petya. So you see, once I provided the program, the rules and facts, I can query it in a different way. I can even query speciality XY, and it would give me all possible pairs, like who can be what. And that shows that you see, in logic programming, we don't have the kind of one path that a program executes, unlike like anything you've seen before. Like in the functional programming, we have one expression which is reduced until we obtain the final result, right? In logic programming, we have this database of facts and rules, and depending on the query, it tries to find the right rules to satisfy the query. And the execution can be quite different based on the query. Any questions so far? Well, I guess the main question should be like, can I program something useful using this technique? Well, because right now it looks like it's kind of a very simple exercise. Well, let's try to program something more complicated. Let's say arithmetics. In logic, you know, the first order logic is used as the basics for defining mathematics, right? If we want to put formal foundations for mathematics, we need to define some kind of abstract concepts and then uh, build on top of them, like make some axioms and then prove something. So the way we can do that, one of the approaches is to use formal reasoning systems. Like we say, the only operations we can do, we can write like axioms, and from them we can deduce something else by following um, substitution steps, like by rewriting terms. And that is exactly how logic is built. And if you want to build like formal arithmetics on top of that, we would need to use some kind of axioms of arithmetics. And those are called Peano axioms. I don't know, probably you should know that. So Peano axioms, they define arithmetical operations. And first of all, if you want to define arithmetics, we need to define numbers, like how we would represent numbers in the formal system. And of course, writing numbers like we normally do, like saying 15, is not convenient. It's like complex notation, which we got used to. It's much easier to define numbers in terms of so-called well, in terms of notation, when we have one constant which is like 0, and we have a term which defines the next element. Let me actually switch to F# for the moment, and I would write this type definition in F#. So I would write my number, and we'll say that this my number can be either 0 or it can be next of my number. Yeah, so if I want to represent, the idea here is that I have the final number of constructions. Like I have the type with only 2 options, and this type allows me to represent infinitely large numbers. So if I want to represent number 2, I would say let 2 equals to next of 0, right? And that would be 2. If I want to define addition using this notation, how I would do that? I would say let rec add x equals to function, and then depending on what I want to add, I would say if I want to add 0 to x, I would return x, and if I want to write to add next of y to any number x, I would return next of add xy, right? So this would define addition using this notation, and I would be able to say add 2, and it would give me 4, right, as a result, next of 0. So that's kind of arithmetics defined in F#. And this is the way actually arithmetics is defined in mathematics, and the way Peano axioms are formulated. This is one of the Peano axioms, by the way, in a sense. If I add 0 to anything, I would get the same thing as a result. This is the first Peano axiom, and this is the second one. If I add x to next of y, this is the same as taking next from add xy. So how can we define this in Prolog? In Prolog is untyped language, so we don't need to define any types. We can just say, we can just operate. So Prolog supports something which is called structural terms, and structural terms is the notation. So I can say in Prolog x equals to f of AB, for example. So this f of AB is anything, but it looks like function with some arguments. I can so those structural terms, they can be also matched. So I can say f of xy equals to f of ab. AB. When I say AB in small letters, it means constants. It means they are like numbers. For example, I can say f of a0. And this would say that to satisfy this, I need to assign x to a and y to 0. If I say f of xx equals to f of a0, it would say me no, it cannot match those two structural terms. So in Prolog, we can have as arguments to as arguments, as values, we can have not only simple values, but we can have also complex values consisting of those kind of terms with brackets and arguments. So it means that if I want to write the same kind of addition in Prolog, well, first of all, how I would formulate the add predicate. In Prolog, everything is predicates. So if I want to add two numbers, I would have the predicate which has three arguments, right? Two input values and one output value. And then I would need to consider two options. Like here, I have two possible options, adding 0 and adding anything else. So here again, I would say I will use 0 for 0. And I would use s of x as the next value of x, just for brevity, instead of next. So if I add 0 to anything, to any x, the result would be x. This is the first rule for addition. And second rule would be like if I add s of x to any number y, I would get s of z, where z is x plus y. So I would say add x, y, z, right? That would be my definition of addition in Prolog. So I would need to load this, and let me see what would be 2 plus 2. So s of 0, s of 0, and result x. You see, it gives me the result 4, which is expected. So how can we get this result? I mean, how Prolog computes this result? Of course, you can see that this is recursive definition, right? But how it is computed? To understand that, we can draw a tree. Oops. What kind of tree can we draw to understand that? So if I say I want to add s of 0, s of 0, and let me put instead of instead of x, the result r, so that we are not confused with the same letters meaning different things, right? So how Prolog looks for result if it has this query? It tries to apply rules. So can it apply the first rule? It cannot, because the first argument in the first rule is 0, and this argument is s of 0. So this does not correspond. Can it apply the second rule? In fact, it can, because the first argument of the second rule is s of x. So what it does, it substitutes this for x, and it substitutes this thing for r. For how do I erase it? Yeah. And substitutes this thing for y. And this rule says that for r, I need to substitute s of z, and z I find from the next call. So it tells me I need to compute add xyz. So x has been substituted for s of 0. Y has been substituted for s of 0. It's the same. And then here we would compute z. And once we compute z, we would put it here and get the result. Now, what happens next? Next, it again tries to apply the rules. And it cannot apply the first rule, but it can apply the second rule. So this can be substituted for x, but for next x. So I would say x prime. This would be y, and this z would be r of z prime. And this would result in add 0 s of 0 and z prime. What happens now? Now it tries again to apply rules, and the only rule it can apply is the first one now, because it has 0 as the first argument, right? So what the first rule says, add 0xx. And here we have add 0 s of s of 0 z prime. So it means that z prime should be equal to s of s of 0, right? It is unified. This process of matching two things together is called unification. So it unifies z prime with s of 0. Then it goes up the recursion and says, okay, z prime is s of 0. So z here would be s of 0. And then r would be s of 0, which corresponds to 4. Right? And that's how the result is obtained. Any questions here? Is it confusing? I would take the silence for yes.
If we would have some suitable rules, we will have some results, yes? Several results.
Yes, if we have, exactly, yeah, that's a great question. If we have several rules that can be matched, in this case, we would have different branches in this tree. So what I have drawn here is called the deduction tree, or the inference tree, and it shows how Prolog obtains the answer. And this is not, in this case, it's not a tree, it's a linear thing. But in some cases, indeed, it can be a tree, and we will see an example in a second. Cool. So what's interesting here, you see, I wrote this definition. I can use it to add two numbers. I can also use it to subtract numbers. I can see add x, s of 0, s of 0. So this would be 4 minus 2. And it would give me the result 2, right? You see how beautiful it is. I can write the definition once, and I can use it both for addition and for subtraction. This is very cool. I can also use it for some more interesting things. I can say add xx s of 0, and that would give me 2. So I would say find x where x plus x equals 4. And let's see for the moment how this works, because this would in fact correspond to the situation when we need to consider different options. So so I say add. Oops, sorry. Oh, it's not working. So I say add. Instead of x, let me put again r, s of 0. So now we have two options, right? We can apply both first and second. Well, not exactly. We do not have two options here, because you see this add RR means that both things should be the same, right? And if I try to match this with the first rule, it understands that x should be s of 0, should be 4. And on the other hand, R should be 0. So it cannot match it with the first rule. It matches it with the second rule. So with the second rule, it means that I need to compute add. And for the second rule, this would be Z. This would be Y. And R would be S of X. So there would be some kind of R prime here. And I would know that R equals S of R prime, right? Then Y would be so it matches the second rule. So Y would be R. And this would be S of S of S of 0, right? So we unstripped one level here. And here again, it cannot match the first rule for the same reasons as before. So it would be again add R2 prime R S of 0. And here we would say R prime equals S of R. In fact, I think I got confused at some point. So once we switch to this rule, in this rule, I think we can match both. We can try to match both rules, right? So if we have the rule add R prime R S of S of 0, we can here go both ways. We can say R prime equals 0. And R equals S of 0. Right? So because in this rule we have R prime as a variable, so we can match this variable with both with 0. So this would be one solution here. R prime equals 0, and R equals S of 0. But this would correspond to, when going back, it would correspond to R equals S of 0. So here, there would be a controversy here. So it would cause this branch to fail because R cannot be equal to things at the same time. And the second branch would be the same as I wrote before, add R2 prime R S of 0. Actually, no, the S of 0. And here again, we would say one solution R2 prime equals 0, and that would add up, and it would result in R being equal to S of S of 0. And in this case, that would be our first solution. So I would say success. That would be a successful solution. And then again, it would be the second branch, which will not again result in a successful solution. So that's how this would be calculated. And if I say here, for example, any number which is not even, it would say that it cannot find any solution. It would try all possible cases and it will not come up with a solution. It's easy before. I can say S of y, S of S of S of S of 0. I can say, please find me all x and y that add up to 4. And it would give me first solution x equals 0, y equals S of 4, then x equals 1, y equals 3, and so on. All possible solutions. And the way this is computed, let us actually try it once more. So if I say add x, y, S of S of S of S of 0. So this is exactly like, it's easier to see it here. So it always matches two rules. So the first time it matches the first rule, which corresponds to solution x equals 0 and y equals, can I write it like 4 instead of putting S of S of 0? I would say 4 in a circle. Okay. This would be the first solution. So first success. And then when we go, when we want more solutions, it tries to follow second branch. So you see, when I ask Prolog to find the solution, it first gives me the solution x equals 0, y equals 4. And then if I press this semicolon, it looks for more solutions. So when it looks for more solutions, it says, okay, it was success here, but let me go back and find more. So it kind of does backtracking. So it says, okay, on this branch we had x equals 0, y equals 4, but on the other branch we would have different values for variables, right? So on this branch, I would say x equals S of x prime, and y and it would correspond to add x prime y S of S of S of 0, right? And here again we have two options. We had first option x prime equals 0 and y equals 3. Another success. And this corresponds to 1 plus 3, right? Because if x prime equals 0, x equals S of 0. And we have this another option, x equals 1, y equals 3. Here x equals 0, y equals 4. Here again, if we have the second branch, we would say x prime equals S of x2 prime. And that would be add x2 prime y S of S of 0. Again, x2 prime equals 0, y equals 2. Another solution. And so on. It is probably obvious that we would arrive to the solution when the last argument would be 0. And when the last argument is 0, the second rule will not match. So it will not match this S of z with 0. So it would only apply the first rule and it would terminate this tree. So there would be a finite tree of options. So that's how nice Prolog is. It can the same predicate once defined can be used for many possible tasks, unlike functional programming. Like for us here we have defined addition. If you want to define subtraction, we would need to write the different predicate, different function. Okay. What else? Of course, I mean, this exercise with arithmetics was only an exercise. Normally, nobody would compute things like that. So in Prolog, there are also support for expressions. The way expressions are supported is that I can say here x equals 1 plus 2 times 3. What it means is that, as I mentioned, Prolog supports those kind of structural terms. So if I write an expression like this, it is converted to a structural term. So I can also say x equals 1 plus 2 times 3, and I would use this built-in predicate display x, which displays it in the form, like in the internal representation form. Prolog supports operators. When I say 1 plus 2 times 3, it knows that those things are operators and they can be written in the infix notation. But in fact, they correspond to structural terms named plus and times, which have always 2 arguments. So it is in fact an expression tree here. You see 1 plus 2 times 3 is an expression tree. And if I want to compute it, I need to explicitly use the specific predicate called is. I can say x is 1 plus 2 times 3, and it will give me the result 7. And this is also an operator. So I can say, in fact, is x 1 plus 2 times 3, and that would give me the result 7. I can say is x plus 1, 2, and it would give me the result. So you see, this is just a syntax sugar. If I write x is something, it's kind of syntactic sugar for writing this. But it makes it easier for a programmer to think about. So if I want to write something easy like a factorial, how I would do that? I would say, okay, factorial of 1 is 1. Factorial of x is f. If I would say x1 is x minus 1. Factorial of x1 f1. Oops. And f is f1 times what? Times x. And then I can say factorial 5x and get the result 120. If I so first of all, this factorial, well, first of all, it's not convenient to write like x1 x minus 1 instead of writing factorial x minus 1 directly. Unfortunately, in Prolog you have to write this. In Prolog there is no explicit computations for anything. So Prolog does not try to reduce in expressions like functional language. It just matches rules and tries to do the deduction, but it does not simplify anything. So whenever you have an expression, you have to compute it explicitly by saying x is something. Another thing which is not good, which I don't like personally about Prolog, is that is only works in one direction. Unlike the example we have seen before, like when the predicate add could in fact use to subtract numbers as well, is cannot be used like that. So is only takes the tree, which has to be completely populated, and it computes the value. You cannot say, for example, 5 is x plus 1. It does not work because it says arguments are not sufficiently instantiated. It means that x should have some value. So I can say x equals 5, y equals x plus 1. This works because when I say x equals 5, everywhere after that, it will be substituted with the value 5. It will be like unified. So this works. If I say x equals 5 here, and then I say y equals x plus 1, this does not work because unification only works in one like query, in one actually branch of the tree. So whenever I unify something until the end of the current like branch of the tree, it keeps this value, but not longer. So this factorial cannot be used to compute, like you cannot say factorial x of 120. It will not work like that because is only works one way. So as soon as I start using is, I lose this universality. If I define my own subtraction and multiplication using the same technique as we did with the add predicate, so add we have already defined, we can use it to subtract. And if we define multiplication on top of that, we would be able to write a factorial which works both ways. Not in a very efficient way though, because the way it would work, it would probably try to it would be a trial and error, but it will theoretically work. Second thing here is you need to be quite careful because, for example, with this factorial, if I compute factorial of 5, it gives me 120. But if I say I want more solutions, I press semicolon, it causes Stack Overflow. You see, stack limit 1 GB exceeded. So it wasted 1 GB of memory trying to do something. Why it happened? Well, it's quite easy to understand why. If we try to draw the tree for this, let me start with something small like factorial 3r. So factorial 3, it says x1 is x minus 1, factorial x1. So it would result in the computation of factorial of 2. And then r is 2, factorial 2 r prime. Let me actually put it in the more so factorial 2 r prime, r is r prime times 2. And then this would result in factorial 1 r prime prime, r prime is r prime prime times 2. Here it is times 3. Sorry. Here what happens when I have factorial 1 r prime prime, it matches the first rule. So it matches the first rule and it says r prime prime equals 1. And this corresponds to the first result. But if I want more solutions, it also matches the second rule, and it results in the computation of factorial 0 r prime prime prime. And this, you can imagine, leads to factorial minus 1, factorial minus 2, and so on. So there is an infinite branch of the tree here, and this infinite branch causes infinite loop and exhausts the stack. So what can I do to avoid this? I can say x is more than 1 here. If I say x is more than 1, then it avoids the second rule if the first one, if the x is not more than 1. So it does not go along the second branch. And of course, like tail recursion also is also important here because this one is not tail recursive and it's not efficient. It wastes memory. If I want the tail recursive version of factorial, the way I do it, I need accumulator. So I would say factorial 1 1. So how would I define this as with accumulator? I need to say factorial x a r. So x would be the argument. This a would be accumulator. So when I go up to 1, I would say factorial 1 a. So it would pass the accumulator to the result. And if I want to compute factorial x a r, I would say x 1 is x minus 1. A1 is a times x, and factorial x1 a1 r, right? But I can load this and I can try how it works. Factorial 5 1 x, it gives me 120 and infinite loop again. So we need, of course, to say x is more than 1 here as well. And because I don't want to, you see here it caused infinite loop without Stack Overflow. Why? Because it's tail recursion. So now we have to stop this on board. Okay, that's good. It does not exhaust the stack. It's just infinite loop. And of course, I need to make the synonym function. So factorial x r is the same as factorial x1r. So here in Prolog, if I have predicate factorial with 2 arguments, it is completely different predicate than factorial with 3 arguments. So I can in fact use the same name, but those would be completely different things. Unlike partial application, which we have seen in functional programming, here different number of arguments means different predicate. Because you cannot like specify less arguments here. Predicate also always has the right number of arguments. Okay, so that is tail recursion. You can also have the co-recursion in Prolog. How will remember co-recursion is when you define a sequence which generates next element upon request. In Prolog, this is very conveniently done by returning next solution. So if I want to generate the infinite sequence of ones, for example, how would I do that? I can say 1, 1, and then I can say 1x, 1x. Let's see how that works. 1x, 1, 1, 1, 1, 1, 1, 1. Right? Very convenient way to generate ones. How it works? How does it work? Let's see. If I say 1x, it first tries the first rule and it causes x equals 1, and then it tries second rule, which says 1x again, and then it tries the first rule again, which means x equals 1, and then it tries the second rule again, and so on. Infinite tree. So that's how it generates infinite sequence. How do I make it 1, 2, 3, 4, 5? I can say 1x, and here 1x equals 1y. X is y plus 1. Right? 1, 2, 3, 4, 5. How do I generate factorials? With factorials, probably we need two arguments. So I would say factorial 1, 1. And then I would say factorial xf. I would compute the previous factorial x1, f1. And then I would send x is x1 plus 1. F is f1 times x, right? One, 2, 24, 120. You see the infinite sequence of factorials. So this can be used like if I want to define the factorial, the first factorial, like for example, my problem is find the number x for which factorial has 5 zeros at the end, like the smallest number x. How would I do that? I would say fact xr, and then I would say r 0 is r mod 10,000. Well, not 10,000, but probably 100,000. 10,000 means 4 zeros. So here it has 4 zeros at the end. So the smallest number of x with 4 zeros for which factorial has 4 zeros at the end is 20. And then if I have more solutions, of course, it would give me more solutions. Any questions here? So this is co-recursion, which is also, it also makes sense in Prolog. Try to, like, as an exercise, try to define Fibonacci numbers using co-recursion, and that would be an interesting exercise. And try to define Fibonacci using normal recursion, tail recursion, and so on. Like this exercise should probably make you, and you make you understand it a little bit better. Finally, let's talk about implementation of lists in Prolog. So lists are very similar to lists in functional language. It's essentially one-directional linked list. So I can use the special structural term which is called dot. I can say 1 and dot 2 and then empty list, and that would be a list of 1 and 2. Why it doesn't work? Maybe I have to put in this implementation of Prolog, it's not called dot, it's in fact this interesting predicate. Anyway, so lists are represented as structural terms in the same way as in fact as in functional programming we have head and tail, and lists can be written like this. So I can say x equals 1 2 3 4 5. That would be a list. Of course it can mix values because in Prolog is untyped language, so you can write anything here, like any constants. This constant which starts with 4 is confusing for Prolog because it's not it cannot understand if it's a number or something else, so that's why I should avoid those. But otherwise lists can mix different types because it's untyped, so it doesn't even know like the difference between 3 and this. And for list support separating head and tail. So I can say x, this vertical line y equals 1 2 3 4 5, and it would give me x equals 1 and y equals 2 3 4 5. And I can say, for example, x y z equals 1 2 3 4 5, and it would give me 1 2 and then 3 4 5. If I say x y z equals 1 2 3 4 5, it will not succeed because I have different number of arguments, right? So this is kind of strict matching. If I have the vertical line, it means that everything, the last variable is so-called tail. So with lists, I can have several common predicates. Like one of them is called member. It's built in, so I can say member 1, like member 3 1 2 3 4 5. It would say true. I can say member x 1 2 3 4 5. It would say give me all members in return. So the way this is defined, I would call it mem to avoid confusion. Is you can say member x if x is the head element. So I can say member x with the list of x and then anything else as a tail. And this variable is called anonymous variable. It's the same as in the functional language. You can use it if you don't care about the value. So, and then member x of an element and then some tail t succeeds only if member xt, right? Then another important element, another important function is append. 1 2 3 4 r. It concatenates two lists. And the way it is defined is I can say append empty list LL. So anything appended to an empty list does not change. And then I can say append XT L XR if append TLR, right? And you can use append to solve several tasks. You can use append to split the list in two parts. So like if you say append XY 1, 2, 3, 4, 5, it will give you all possible splits of the list. So if you have the problem like get rid of the last two elements or three elements of the list, how would you solve that? You would say here, like if it's two elements, you can say like this, and X would be equals 1 to 3, right? If it's three elements, you can say like this. If it's 100 elements, you can say append XY length Y2. Okay. What if you want to use append, like maybe somebody who is not completely lost can tell me like how can I find the element next to a certain element in a list? So for example, I want to give the value of 2 and find the next element 3. How would I do that using append? Anyone? So you see, append generates all possible like combinations of lists, right? So if I write another condition here, so if I say y should start with 2, right? If I write something like this, it will give me the only one solution, because the way it works, it tries to generate the like x equals empty list y equals 1, 2, 3, 4, 5, and then it checks, does y start with 2? No. It rolls back, it tries another combination for x and y, and when it gets the right combination where y starts with 2, it succeeds, and that's why it gives me back the result like this. So if I want to find the next element after 2, I would say y equals 2 n, and it will give me n equals 3, right? And if I want to write it in the more compact way, I can write it directly in the query. I would say I don't care about x. I want here 2x and then something else. And that would give me the solution x equals 3. How do I find the last element of the list using append? I can say like this. This gives me 5. So this is exactly as in the functional programming. If you want to find the last element of the list, you have to traverse the list till the end. So append does the traversal of the list. So that's not an efficient operation. If you want first element of the list, of course, you can use append to do that. But it's a very bad style to use append, because you can always find the first element of the list by just saying x with tail equals 1, 2, 3, 4, 5. You cannot use other, like if you put like here x would be the tail, not the last element. I hope that is clear. And you cannot use this, because if you use this, it assumes the list of 2 elements on the left. So you can only use this vertical line to match some head and the rest. So if you need to do operations like multiply all elements of the list, add all elements of the list, here we do not have folding, we cannot easily pass functions as arguments to predicates. Well, in theory, somehow we can, but that's not normally the style of logic programming. So in case you have a problem like multiply all elements of the list, you need to do it like manually, right? You can say mult x equals x, and then mult x with the value of with the tail of t equals r if mult t z r is z times x. So something like this. (24). And if you want to make it tail recursive, you should be able to make it tail recursive. Please practice doing that till next time. That's something you might be asked during the final test. Write this in two possible styles, tail recursive and not tail recursive. Okay, any questions that you have? So I know there have been quite a lot of content today. I will give you a link to watch. No, actually, I wanted to give you one more example. Sorry about that. Yeah, one more important example to show that in Prolog you can easily manipulate expressions. Consider like let's see this example. Consider the following problem. You have the circuit with resistors like this, which is a combination of parallel and sequential combination of resistors, and you need to compute the resistance of this circuit. So let me put this thing here, and this can be 1, 2, 3, 5. So suppose I have the circuit like this. I want to compute the resistance. You can probably understand that this circuit can be easily represented as a tree, right? So this circuit, I can say R equals to sequential combination of parallel combination of sequential combination of 2 and 3 and 5 and 1. So this defines the circuit, and this seq and par is just structural terms, just the names I invent. I can put anything here. I just invent them. So to compute, I need to define the predicate. So like resistance of sequential combination of A and B would be R. If resistance of R is RR, resistance of B is RB, and R is RA plus RB, right? This is for sequential, and for parallel combination, it would be Ri times Rb divided by Ra plus Rb. And then I need to say resistance XX to account for any other resistances. So now let's define this and see if it works. Resistance of, resistance of this R. Yeah, it gives me 3.5. Good. So you see the good thing here is that to solve this problem, I don't need to do anything complex. I don't need to define the data type. I just agree that I would define the sequence by using this kind of notation. Now, a question to you. What will happen if I substitute is for equals? It looks like it's still valid, right? It is like I can unify. If I load this, I do not get a syntactic error. So it is kind of valid thing to do. What will be the difference if I now give this query? Who can guess what happens?
It will overflow, maybe.
Overflow. Look at this. It gives me back the expression. Remember, I said that if you want to compute the expression, you need to specifically call is. And if you say equals, equals means just unification. So whenever I say here R equals Ri plus Rb, it takes the two expressions and it just glues them together, like it defines the structural term with the plus, and it keeps everything in the expression form. So you have this expression. And even here, you do not need to use numbers. Like you can use R1 as the constant, and it would compute you. It would give you the expression how to compute the result of this arbitrary circuit. You see how nice it is. And if you want to make it a little bit more usable for like for people, you can define also operations. You can say I want to define operator. I would not go into details on how this is done, but let's say I want to define this operator for parallel circuit, and I want to define this minus minus for sequential, and I want to define this kind of line for resistance. In this case, I can say when I say x of x, it means infix operator. So I can say a sequential b and this gives me the resistance R. A gives the resistance RA, B gives the resistance RB, R equals RA plus RB, and then the same thing here. A parallel B gives the resistance R if, and I will copy those two. And then I would need to say X gives the resistance of X. So what is wrong here? I'm still having some problems here. Why? I think I need to be more careful with. Anyway, so let me not waste the time here, but when you define operators, you need to be very careful with this kind of first argument, which is like it's the priority of the operator, and priority defines like how would you how it behaves relative to other things like plus and minus. So it needs to be consistent with other priorities, otherwise it will not. It will be, for example, if it has higher priority, then it might confuse like the Prolog engine. Or maybe I just cannot use some of the operators in this manner. Maybe this minus is not. Let me just use normal minus for minus. Oh. Anyway, so it is possible to extend Prolog language by using those kind of constructions and define arbitrary, like domain-specific language. Like, for example, for people who deal with computing circuits, they might use this language to handle their tasks, which could be defined on top of Prolog. So that's it. I will give you. It is covered also in one of the video lectures. I would give you a video lecture to watch for the rest of today. Try to practice a little bit using all those kind of list operations. And next time, I will welcome any questions from you. At the final exam, there would be some simple problems like dealing with lists. And there might be, for those of you who want higher results, there might be some problems dealing with expressions as well, something like taking arithmetic expression and converting it to different notations, or just replacing all numbers with zeros in the expression, something like that. Try to make sure you understand that arithmetical expression is a tree. It's not something magical. It's not a list. It's not a string. It's the tree of structural terms. Okay. Anyway, any final questions, thoughts for today? Okay. Thank you. You have the recording of this lecture, and I will send you a couple of more videos to watch.
Bye.
Bye-bye. Have a great day.